Hi everyone, welcome to the UCL East Lunch Hour lecture series. So this week's lecture is going to be on Towards Net Zero, life cycle assessment as a decision-making tool for low carbon solutions. So I'm Kate Jones, I'm Professor of Ecology and Biodiversity in the Department of Genetics, Evolution and the Environment. And I've got the real privilege of chairing this lunch hour lecture for UCL East, and I would like to welcome our two amazing speakers that we have with us this week. So the first is Professor Paola Lettieri. She's the Academic Director of UCL East's new campus in Stratford, which is called UCL East. Professor Paola Lettieri has joined UCL in 2001, and she spent about 5 years in R&D at BP Chemicals, and she was a research fellow of the Royal Academy of Engineering at the time, which was the first female engineer to be honoured with such a prestigious award. So very lucky to have her here at UCL. She's an international expert in fluidization and life cycle assessment, and she uses those methods to apply these to chemical, nuclear, waste management and the energy sector. So her work of her life cycle assessment group here at UCL has aided the development and scale up of industrial energy from waste processes, influenced plastic waste management strategies, and determined radiological impact of spent nuclear fuel reprocessing for the very first time. She was a recipient of a prestigious senior research fellowship at the Royal Academy of Engineering and Leverhulme Trust for her work on nuclear waste management and life cycle assessment. And she's published over 250 papers, and she's a fellow of the Royal Academy of Engineering. So our second speaker is Charnette Chow. She's a research fellow at the UCL Plastic Waste Innovation Hub. So Charnette has an MPhil in biochemical engineering, and she specialises in applying life cycle thinking to analyse the environmental impact of products and systems. So her work really focuses on the application of this life cycle assessment across multiple sectors. So these include forestry, consumer packaging, construction, and healthcare. And she advises on the sustainability of new interventions and implementations. So she's working in a multidisciplinary manner, and her life cycle assessment work aims to provide kind of the evidence base that we really need for governmental and industrial policy making. So welcome to you guys, and thanks very much for joining us on the lunch hour lecture. So just before I hand over to them though, I just want to let you know that we'll have some time for questions at the end, and these questions can be submitted at any point during the lecture. So if you go to Slido and enter the event code #UCLEast, the details I think will be put in the chat just now for you to add in your talk. So you can add in any questions at any time, and we'll answer those at the end. And remember, on Slido, you can upvote any questions as they come in. So if you see one that you particularly want answered, then give it a thumbs up, and I'll prioritise it. So I'd really like to pass over to our amazing speakers now. So Paola and Charnette, over to you.
Thank you very much, Kate. Can I just check that you can hear me well and you can see my screen? Wonderful. Thank you so much for the introduction and really for the invite to talk about the research that we have been doing in chemical engineering and as part of the Plastic Waste Innovation Hub. So the context of this talk is really about sustainability, and really how do we, just trying to change slide, yes. It's about sustainability and how do we make decisions that address the sustainable development goals in achieving a better and more sustainable future for all, while of course preserving the ecosystem. I really like the diagram that shows on the left-hand side the ecosystem services because it's there to remind us about the many and varied benefits that we as humans get from nature, and really in all of its functions, from provisioning, regulating and supporting our development, and enabling us, of course, to develop also as a cultural society. So between the Sustainable Development Goals and the ecosystem services is really a reminder of the environmental degradation that we have been witnessing over the last couple of hundred of years, in particular, while the socio-economic development of our contemporary society was happening. So on this slide, you're basically looking at 12 indicators that are there to capture the major features and changes that have occurred in the last couple of hundred of years, whether you're looking at urbanization or even to the degree of globalization and connectivity that we have been able to achieve. Obviously, all of these development comes with a cost. And perhaps at the time we didn't know that there would have been an obviously attached to this. But planet Earth, as we know, has witnessed an incredible change, and the human pressure on the Earth system has really increased exponentially again since basically the economic development has increased. So these diagrams are there to show you basically the great acceleration that in some of these effects has been seen since the mid-50s. So the Anthropocene now effectively is threatening the stability of the Holocene. So we're all aware that the relationship between the rising concentrations of greenhouse gases in the atmosphere and global warming. We're all aware of the target to basically limit warming to 1.5 degrees since prior to industrial development. And what you see on this diagram is basically the observations and the modeling related to a 1 degree global warming change and how that compares with the 1.5 degrees C, which we are targeting at the moment, and what it would actually look like if we were to exceed 1.5. So clearly, unless we limit global warming with strong actions so that we reduce CO2, methane, and other greenhouse gases emissions, then we run the risk that limiting warming to 1.5 degrees C will be beyond reach. So we are at a point where we have entered a very important decade where we need to stop that exponential increase and we need to basically bend the curve so that we can continue to evolve as a society, economically, socially, and continue to thrive, but maintaining the Earth system within a safe set of planetary boundaries. And this is a concept that was introduced back in 2009, and the graph is referenced to a paper in Science in 2015. So what the authors have done here is to propose 9 planetary boundaries that should really guide the way humans behave during the Anthropocene. So here we're basically looking at climate change, ozone depletion, and acidification, which relate to climate. And then we've got a number of other slow variables, as the authors have called them, that basically are there to regulate the capacity of the resilience of the planet. So here we've got the land system change, the fresh water use, the biosphere integrity, but there are also nitrogen and phosphorus. And we've got a couple of question marks on this graph because relate to aerosol loading and chemical pollution, which are still difficult to quantify. So the way to read it is to basically look at the green zone, which highlights the area of basically low risk, and then the yellow zone, which basically shows the area of increased risk and uncertainty. And then the red zones are obviously what need to be addressed quickly, because basically they show that we have already transgressed 3 of these boundaries. So what this is all telling us is that business as usual is really not an option anymore. And so it's about investing in transformation so that we can move quickly from a fossil fuel economy to a green carbon economy. So net zero means effectively a huge amount of technology transformation that has got to occur in the next 10 years if we want to basically achieve the targets that we have globally committed to. And this is not a small task because it means emissions from homes and transport and farming and industry will have to be avoided completely or offset by planting trees, for example, so to remove CO2 from the atmosphere. So Charnet later, for example, will show you how we have applied a life cycle assessment in a study with the Woodland Trust in relation to afforestation. So here the challenges then related to the transformation of the transport system, so with electric vehicles and carbon capture and storage, and of course, more green power. So what have we said so far? We're talking about effectively a simple relationship between the growth in population in our affluence. It's all underpinned by technology, and we have seen the impact that this has had on the environment. So technology underpins what we are able to do today, and as we have seen in the previous slide, also what we need to put in place so that we can revert basically the exponential situation we are witnessing. So it is the T that we are interested in, and it is the technology that then uses the assessment of really the new technologies that we use the life cycle assessment methodology for. So LCA, in short, is basically a standardized methodology which enables us to assess the environmental impact of a new process, a new product, or a new service that is put in place so to address the problems that we have been talking about. So this effectively means then adopting a life cycle thinking approach, whatever is the question we are addressing, means looking at the resources needed for a new product or process, the material processing, the manufacturing, the distribution, the use and end of life. So the entire life cycle needs to be assessed. And the LCA enables us to basically identify at every step of this life cycle what needs to be improved so that we basically enable the technology transformation that we have been talking about. Clearly, along the life cycle, we need to be able to maximize opportunities for recycle, reuse, and recovery, so to improve the situation from where we are. So what I've got on this slide is really a reminder of the Sustainable Development Goals. They talk to us not only about the environment, but really the three level and the complexity between the social, economic, and ecological systems, which are all intertwined. So life cycle assessment comes to help really at all of these levels, whether we are applying environmental life cycle assessment to assess the environmental impact of new products and processes, or whether we do work with the social life cycle assessment to basically assess improvements related to societal issues. And equally, the life cycle costing then addresses the economical level. So when we look at the application of the LCA, here we basically have a choice, and it depends on what kind of question we are trying to answer. Whether it's about a particular product manufacture, then the boundary is all related to that. And so the problem is actually a small one from gate to gate, as we say, was whether actually we are interested in a slightly bigger analysis from the extraction of raw materials to the processing and manufacture, or whether actually is the entire life cycle from cradle to grave. And so it becomes really a very large problem that the life cycle assessment then can help analyze on all of the steps. Applying life cycle assessment means answering questions. And so the LCA will give us an answer depending on what the question is and what we are actually trying to quantify. So if we are interested in the level of SO2 emissions from a particular process, then we could be looking at assessing the acidification potential. So what we call basically looking at a midpoint in the cause-effect chain, or otherwise look basically at the societal concern that comes with SO2 emissions, which is directly related to the loss of biodiversity. So again, depending on what we're trying to answer, who the audience is, then we would be applying a life cycle assessment and define the impacts that we want to determine accordingly. So we have been doing LCA for 15 years plus now, and we have been tackling many different questions. And proud to say that we have been working with many different sectors and industries. What we have got on this slide is really the currently active research projects that we are involved with. And with CharNet, we're going to give you a flavor for some of these examples, not all of them. And it's really about more than the results themselves. What kind of questions have we tried to address and how have they been used? So I'm going to give you an example of geothermal energy and also the work that we have been doing with the National Nuclear Laboratory in Sellafield, looking at nuclear waste management. And CharNet will then take you through two recent examples where we have applied LCA to the single use of masks versus reusable face masks, and also the work that we have been doing with the Woodland Trust. So first of all, this is an example about geothermal energy. So why geothermal energy? We said that we need to move from a fossil-driven economy to a green economy. So this basically means trying to amplify effectively the range of clean energy that we can access. So we have, with funding from the European community, we have been involved on a large-scale project which has looked at the life cycle assessment of the Hellishady plant in Iceland. So this is the first time that an LCA study is done on this plant. It's a geothermal plant. So this is actually one of the largest combined heat and power geothermal complex in the world. It produces 300 megawatt of electricity and 133 megawatt of hot water. In the big context, geothermal energy contributes in a very small way these days. So only with 0.3% really of the global electricity production relies on geothermal energy today. However, in order to achieve the targets that we are aware of, it is expected to increase 5-fold by 2040. So geothermal energy basically targets heat, which is stored in the Earth crust, to generate clean renewable energy. So typically, this means excavating 2 deep wells, which are used to basically inject cold water, as it is shown in this picture, if you look at the well under number 1. And then basically there is a production well which takes the hot water, which is mined from the rocks underneath the crust, and the hot water it comes to the surface and it is used to produce electric energy in a steam turbine. The condensed water is then pumped back down, and so you have a cycle. So the construction of this kind of plants then requires deep down wells with a lot of steel casing. So the life cycle assessment that we have done wanted to look at what we call the hotspot analysis. So wanted to identify basically which phase in the construction, in the operation, and also in the end of life basically contributes to the environmental impact. So this diagram, I'm not going into great detail and not expecting you having to understand all the details of it. But if I can get your attention to look at the red bars, basically this tells you that the construction phase is basically the phase that has got the highest environmental impacts. And this is related in particular to the use of steel for the casing when drilling the as I was showing you earlier, sorry, just trying to the wells. So, okay, it's working. For a moment, I thought that the screen had stopped. Okay, so we have used basically that understanding then to take the study closer to home. And we have worked with an engineering company that is delivering the United Downs Deep geothermal power plant in Cornwall. So this is the very first geothermal plant in the UK. So geothermal engineering is developing the plant, and I've co-authors the papers that are on this screen. So the learnings from the Hellishady plant basically showed that construction is where we need to basically do our best to minimize the environmental impact. So, for example, reducing or increasing the amount of recycled steel for the casing, but also reducing the use of diesel engine machineries during the drilling and the various construction phases, and replacing them with electric vehicles, for example, electric systems. The question we have asked, and which basically is shown on this graph, is different, and it's how does geothermal energy compare with other intermittent clean source of energies that can be wind and solar, for example. So when you look at the diagram, you basically see that if you take climate change at the top, nuclear has the lowest carbon emissions. And if you look at the plant in Cornwall, then, which is the red one, is basically the third the third type to give you the lowest carbon emissions. However, what has to be noticed is that depending on what impact category you are interested in, and that depends on the particular question that LCA is trying to answer, so whether it's climate change or ecotoxicity or human toxicity, then the ranking between the different types of energy changes. So there isn't a single answer that actually LCA can give you, but depending on what you are looking at and what particular step in the process then you're trying to improve, then you would be looking at the impact category, which is mostly relevant to that, and the LCA would be guiding you on how to improve basically that impact. So I've just shown you that nuclear is basically the cleanest of the types of energy systems that we could be using. And as we know, in order to reach net zero, nuclear is expected to provide more energy than currently does. So just trying to move this away. Okay, so what I've got here is basically a diagram which shows the problem related with nuclear energy, and which is about nuclear waste management. So how should we deal with the solid nuclear wastes? Should we go for a direct disposal, or should we reprocess the spent nuclear fuel? And what is the effectively dirtiest step in the cycle, whether it's direct or reprocessing? And how can these implications be quantitatively analyzed? So this is the kind of questions that, again, the life cycle assessment methodology can help us with. When we look at nuclear energy, sorry, my screen has frozen. Okay. We basically are then looking at different potential scenarios so for nuclear waste management. And this is really whether both plutonium and uranium are disposed, which basically means having a geological facility, depository, the disposal facility, or whether we are actually disposing of plutonium by recycling uranium or recycling both, or again, doing something different. So here we have worked with Sellafield, with the National Nuclear Laboratory, with the Nuclear Decommissioning Authority as part of the distinctive project sponsored by the EPSRC. And we have applied a life cycle assessment to all of these 4 scenarios with the view of basically enabling then the decision making of what the next step needs to be, whether it's for reprocessing or whether it is for an open cycle. So first of all, this is a tricky area of work because there wasn't really a methodology available that would enable to determine in a life cycle assessment context the radiological impacts of radionuclides from nuclear waste. So this has really been at the heart of the problem that we have tackled. And Andrea Paolillo's PhD thesis really has tackled this. And Andrea has developed a new methodology, UCRAD, that enables now to determine the radiological impacts of radionuclides in an LCA context. And then what we have done is to apply that methodology to scenario number 3 from the previous slide, which basically says what kind of impacts would we have if we were to apply a scenario in the UK where both plutonium and uranium are recycled. So the way to read this diagram is basically that if you are reprocessing nuclear waste, then all of the non-radiological impact categories are rather happy and actually happier than the disposal because they all have lower impact. When we, however, look at the ionizing radiations, then this is the case where the direct disposal then has significantly lower emissions than the reprocessing, because of course in this case we're basically burying underground in a geological disposal facility all of the nuclear waste. So at this point I shall ask Charnet to take control of the screen so that she can take you through another couple of different examples to show you how we have applied the life cycle assessment.
Cool. Thank you, Paola. I hope you guys can hear me. I did unmute myself, so it's good. So I'm a research fellow working at the UCL Plastic Waste Innovation Hub. So a bit of background of the hub is that we're a multidisciplinary team of researchers that includes scientists, engineers, designers, social scientists such as behavior science, etc. And we all tackle plastic waste issues from different angles. And the hub essentially aims to provide research-backed recommendations to assist decision-making and to inform policy as well. So the 2 case studies that I'm going to take you through, the plastic street shelter was helping the Woodland Trust revamp their tree planting policy, and then the face mask is to try help us decide which is better for us, better for the environment for us to proceed with regards to masks. Let's see if this is work. Yes, so before diving into the Woodland Trust case study, let's talk about carbon sequestration. Trees are great for storing carbon, and depending on the age, the size, and what type it is, they do vary in terms of how much they can absorb each year. As you can see in this table, the tree range from 10 to 50, and they each, so the older they are, the bigger they are, they do absorb more trees annually. It's not absorb more trees, carbon sequester more annually. So if we take, So if we take the carbon dioxide that was emitted in 2019 in the UK, we amounted about 450 million tons of CO2. And what is that in relation? That's how many trees would we need to sequester all these carbon? This will amount to about 4 billion 50-year-old trees or 27 billion 10-year-old trees. And considering back in 2015, our woodland area was about 13%, woodland cover was about 13%, and that was equivalent to 3 billion trees. We definitely don't have enough trees in the UK to sequester the amount we emit at the moment. So going to the Woodland Trust case study, we were approached by the Woodland Trust back in 2019, talking about the net zero goals of the UK, and they have translated this to us requiring about 1 million new acres of tree cover to assist with the net zero goals, combined with other initiatives that we have. But this is equivalent to about 2 billion trees, planting 2 billion trees more. But the issues for that is that most trees require being grown at tree nurseries before being planted on site with plastic tree shelters. So the main question that the Woodland Trust gave us was that, does the environmental impact associated with using tree shelters outweigh the benefit of having new trees? If we are going to use tree shelters, whether or not it should be recyclable or biodegradable, or what other end-of-life options do we have with for using tree shelters? So for us, whilst we set the goal and scope, we wanted to capture, there were key things that we wanted to capture, including making sure that we compare planting trees with and without shelters, comparing different types of shelters, whether are currently available or what are the future options of tree shelters as well, and then comparing different combinations of waste treatment for these, as well as considering the carbon sequestration of new trees. The research carried out include going on site visits. So we went to a tree nursery to look at how trees are grown in nurseries. So that's part of the life cycle of new trees. So as you can see that they're grown in nurseries where they're being plotted in trays before being sent on site for planting. So we also did some literature review in terms of how shelters do degrade under weathering or grazing, the fragmentation rate or mineralization rates. But we also looked at, did interviews with some stakeholders in terms of how best or what are the logistics of collecting these shelters for waste disposal as well. So that is all part of our data gathering to set up our scenarios. As you can see, this is our system boundaries. And first of all, the first thing that we wanted to look at is growing trees without shelters. So this is in the green box now. So what we considered for this is the material sourcing for growing trees at nurseries before delivering it to planting sites, but also considered the removal of any packaging that is needed to transport these trees. And then we looked at multiple scenarios that include tree shelters. So conventional tree shelters, bio-based tree shelters, or biodegradable. We looked at that and combined it with different end-of-life treatments. So recycling, landfill, incineration after 5 years of using it. So to be able to compare planting with shelters and without shelters, we need a functional unit so that we can compare it. And that is a single tree surviving past the 5 years establishment period. The reason why we chose 5 years, it's because under current guidelines, tree shelters need to support tree growth for 5 years, because after 5 years, the annual survival rate of a tree is near enough 100%. So it's freestanding already. So that's why we did that. To be able to grow, so normally looking at survival rates, we need plant 2 trees to have 1 tree survive without shelters, and about 1.2 trees to grow, to plant 1.2 trees with shelter support to have 1 tree surviving after 5 years. That's the that's the stat that that's the assumption that we use for this study. So in terms of climate change results, there's a lot of results here because we did do a lot of scenarios, but I want you to focus on the green. The green is the no shelter. As you can see, planting trees without shelter will have the least the least climate change score compared to the results generated by planting trees with shelter. So as you can see, there's we did a lot of, as I explained previously, we did a lot of different scenarios with shelters and like how they are treated at the end of life. So current scenarios in terms of how they degrade already, or what if they are fully collectible for incineration with energy recovery and recycling. But having said this, if we look at how much CO2 a tree could sequester by just planting it. So by age 5, a tree would have cumulatively sequestered 32 kilograms of carbon dioxide, which is a lot higher than how much is used to plant trees with shelters in general. So in this case, in the climate change impact category case, planting trees with shelter does not outweigh the benefit of a tree being grown itself. However, we do need to look at other environmental impacts. So the potential microplastics. So from literature, we calculated that with degradation rates, so like fragmentation, so how much it fragments by UV radiation, by being under the sun, but also how much gets taken up by microorganism in the soil. So we call that mineralization. So if we take into that account for conventional shelters, it's about 50 grams and 60 grams for PLA shelters if they were used on after 5 years. But if they don't mineralize or they don't get taken up, then it'd be about 80 to 150 grams of plastic being left on land and not being able to be collected after 5 years. So if we scale this up to 2 billion trees, this would be a lot of plastic. As a whole, what we did was there are trade-offs in terms of environmental impact. So other impacts that we look at includes acidification, land use, water use, eutrophication, and so to get an overall environmental impact score, we normalize these results using planetary boundary or global carrying capacity normalization factors that were developed by the European Commission. And then also weighted it accordingly in terms of taking into account of expert and public opinions on which environmental impact are most important, and also the robustness of evaluation as well. So as a whole, planting without shelters does come out the most environmentally beneficial, but then bio-based shelters does come out as the least, mostly because of the aggregation, the agriculture needs of planting biomass to support the making of PLA shelters. But of course, if bio-based shelters were to be made of bio-waste, then the impact score will also be reduced. So this could be something, another next study that we could have a look at in terms of future scenarios of shelters. So yes, as a whole, from our study, we do say that planting trees without shelters is recommended before recommending using shelters, and being able, the waste management system wise, we prefer shelters to be recycled before it's incinerated for energy from waste. So incineration with energy recovery. A caveat with the study is that it doesn't consider the ease of planting trees in terms of going up to the land. So this is for, so we want to emphasize that the life cycle assessment does inform how to inform decision making in a way where we need to consider other factors besides the environmental impact, because sometimes if it's harder to access the planting site, then maybe tree shelters is needed. But if it's accessible and you can go back and plant trees, then it might be better to not use shelter. So, moving on to the next case study. So back in 2020, or ultimately, we're still technically in this pandemic, well, we see increased use of single-use face masks. And it sparked our initial case study on single-use versus reusable masks for the public, purely because also that there was a shortage on single-use masks at the time. So as the hub wanting to make recommendations on whether single-use versus reusable masks is better, we did a multidisciplinary analysis which considered the technical efficacy, the costs, the behavior, and also the environmental impact of using masks as well. So Paula and I were part of the life cycle assessment team to look at reusable masks versus single-use masks. And what we assumed was that what if everyone uses one mask per day for a whole year? This will mean that everyone will use 65 surgical masks and but only 7 to 12 reusable masks per person if we assume that the mask can last 30 to 50 washes. So now that will then bring down the waste arising will decrease dramatically. We switch from surgical to reusable masks, over 80% reduction of waste. And in terms of climate change, we looked at different scenarios of how we can supply surgical masks. So whether or not we supply surgical masks from China, Turkey, or the UK, but sourcing materials differently. We saw that sourcing masks more locally, or surgical single-use masks more locally, would be more environmentally preferable. But for the reusable mask scenario, we also looked at whether we should hand wash the mask or use machine wash the mask. So ultimately, we think, so our study shows that reusable mask is more environmentally preferable, especially when especially if we machine wash the mask, as that will be more efficient in terms of water use and electrical use as well. Cool. So, how does that now? What about in healthcare? So, since we published that study, the study got a lot of traction in terms of doing more on the healthcare side. So the NHS have pledged to become more carbon neutral by 2040. And because of the PPE waste arising due to COVID, there's a lot more pressure in terms of wanting healthcare sector to reduce the single-use waste. So a lot of project partners came to us in terms of asking what are the actual environmental impact associated with mask use in the healthcare sector. But also now that shortages of single-use masks isn't an issue, what is the most environmentally preferable way to supply masks? So is it to minimize supply chain impacts of single-use masks, or reusing single-use masks by decontamination, or outright employing reusable masks? So to scope out the study, we realized that different masks are used for different situations. So medical graded masks, such as the surgical mask, are used in preventative situations, so a low risk situation in healthcare. But in high risk of infection area, they use PPE graded masks. So FFP3 mask was recommended for healthcare worker before shortages arises. So we're going to focus on PPE graded masks, as we talked about surgical and cloth masks previously. But the three scenarios that we looked at was using the FFP3 mask, use once and dispose, and then talking to our ICME partners, they said that decontaminating FFP3 masks via vaporized hydrogen peroxide to be the most effective. And that tends to mean that they can be reused 5 to 21 times. And also there's the option of using reusable solid half mask, where the mask can last more than a year, but for this study, we assume the lifespan of the mask is 1 year, but the filter change could be either monthly or up to 6 monthly, depending on the breathability of using the mask. But of course, this is reused via wipe clean using antibacterial wipe. So the system boundaries for this, I can take you through clearly. Again, the red box shows the single-use mask. So the FFP3 mask, we considered sourcing the materials, manufacturing of the mask and the packaging, as well as the waste bag, because all masks are treated as clinical waste. So they are put in clinical bags for incineration. So this is the so the first scenarios, and then we looked at the reusing FFP3 masks via decontamination. So we considered the manufacture of cleaning materials as well, and like disposing of these cleaning materials. And thirdly, for the reusable half mask, we included the replacement of filters and straps when they get loose, so that they can continue to use the mask, but also the manufacture of wipes and disposal of these wipes as well. To be able to compare all three scenarios, the functional unit used for this was 1 year of mask use per healthcare worker. So this assumes like 240 shifts a year, and a year, but 7 to 12-hour shift meant that they will need to put on and take off the mask twice in one shift. So the climate change result is very telling, pretty similar to the previous graph, where single-use mask being sourced differently. You can see that sourcing locally is more environmentally beneficial, but reusing FFP3 masks and using reusable half masks is more environmentally preferable in the climate change impact category. And to be honest, it's pretty much the same in other impact category as well. And of course, the more you reuse the mask, the less impact it has. But we recognize that the amount of time that you will reuse the FFP3 mask or reuse a filter is dependent on the person, depending on how easy it is for you to lose a mask, or even how you feel about reusing a filter that's been installed for however long. So there's other factors that will come into play in terms of the actual environmental impact of using reusable masks. So in terms of waste arising, as you can see, single-use face masks will have the highest waste arising, and this considers mask, packaging, wipes, and disposable bags. And here you can see that, okay, for reusing FFP3 masks, it is lower, but actually the waste arising from using solid half masks, reusable solid half masks, even will have the lowest waste arising as a whole. So this also further shows that we can't just use climate change results to make decisions in terms of which scenario or which mask option that we want to employ, but you need to take into consideration other factors as well. So as a whole, reusable and reusing mask is more environmentally preferable. If we are to use the traditional FFP3 mask or even surgical masks, we should be sourcing them more locally to lower the impact, and the choice of which reusable option to use does depend on reuse behavior and logistics as well. So I'll pass this on back to Paola.
Thank you, Charnet, and I am aware that we have used quite a lot of the time, and we would like certainly to leave time for questions. This talk, it's basically part of the UCList series of the lunch hour lectures at UCL. So with my UCList director's hat on, I simply wanted to finish off by saying that UCList is opening next year in September 2022. The context of this talk has been sustainability, and UCList is our Sustainable Living Lab campus at the Queen Elizabeth Olympic Park. It is where we will be launching, in fact, in the context of what you've just heard us talking about, a couple of sustainability modules to teach our students at UCList about the tools to make decisions for a sustainable future, but also teaching life cycle assessment with the multiple applications as examples for learning. In relation to the Sustainable Living Lab campus, it's perhaps a novel way of, a different way of describing the university campus. So we are at the Queen Elizabeth Olympic Park, and the plan at UCList, I like to say, is that of has been that of creating and therefore also managing the campus as a living landscape. And our Kate Jones, who is with us today, she's actually been in the driving seat as the expert in ecology and biodiversity to ensure that we develop a living landscape strategy at UCList that benefits the park itself, but also that enables us to take advantage from sensoring and learning from the park and the way nature in the park adapts to changes. So there is quite a lot to come that we are really looking forward to as we open next September. But today is also the day when the London Legacy Development Corporation is launching Shift, so the new innovation district at the Queen Elizabeth Olympic Park, of which UCL has been one of the founding partners. And the vision really relates to what I just said in the previous slide. It's really about the park being London's living test bed, as we've been talking about the need of developing technology, developing low carbon technology. We've got to test the technology and include the public in that testing so that the technology responds to really societal questions and challenges locally and obviously then globally. So I'm going to leave this here so that we can take some of your questions, and hopefully I have stopped sharing.
Thanks, Paola and Shana. That was absolutely brilliant. Really, really great, and really topical as well with all of the things that are going on with the pandemic and tree planting. So it was really fascinating. So thank you very, very much for that. We've had so many questions. I'm not sure we've got time for all of them, but I'll do my best because it was really fascinating. So there are a couple which I kind of grouped together actually, because they're kind of asking about whether we can use this LCA process as a virtuous feedback loop, so that, can we change societal opinion? On the flip side, can you stop companies from greenwashing and claiming they're doing it? And also, how does it feed into this, the lots of passion and need for a circular economy? Thank you.
Okay, thank you, Kate. Yes, it's many questions into one, and the simple answer, I suppose, is yes to all of them, in the sense that life cycle assessment is certainly one of the methodologies that, because it can quantify and predict the environmental impacts of any transformation that we are aiming to achieve, then yes, it can spot greenwashing if obviously what is being declared is not actually right. And yes, I mean, it is what can enable that change in society and in the way we behave, because it can actually alert in the way, Charnet, for example, has been presenting in relation to the single versus reusable masks. One can demonstrate the impact of using one type versus the other, but also the impact of how we dispose of them. And it's not just about technology clearly or environmental impacts. It's actually very much about educating ourselves and the public on behaving differently, so that the way what we do impacts, in the world around us, needs to change, but the change needs to start from what we do.
Janet, would you like to come in?
Yeah, I find the question quite interesting, because I'm always thinking, because I have to say that life cycle assessment is as good as the data you get from it. So in terms of greenwashing, like it's very hard, especially for a company, to give us all the data to like monitor, like to evaluate the processes. So yes, we can like try, as long as we got the data to model like how they run their processes. Of course, we can like diagnose where are the environmental impact lying with, but of course, if there's like a privacy wall, it's very hard to also analyze that as well. And in terms of providing change to societal opinion, I think it's very a scientific way to showcase what are, how we can proceed in terms of being more sustainable, and like doing these like product or processes evaluation is quite interesting way to showcase that. And I guess it's also more about like education in terms of the public, how life cycle assessment work as well, so that they can understand the results and how it's carried out in terms of the process and assumptions. So yeah,
I think that's a really great answer, and I think it kind of maybe if we ask one of these other questions, because it's quite related, and it's like, the question was about how reliable life cycle assessments are in making these assessments and predicting future environmental impacts. You kind of hinted there that you needed all the data, so perhaps maybe we could talk about that.
That's exactly right. It's life cycle assessment sits on a very simple set of algebraic equations. It's not really complicated to perform. The complexity is really getting the scenarios right and actually getting the real data to work with. And this is why we feel that we have been able to make a little bit of a difference with all of these studies, because we've always been working with the industry that was leading basically that product or process development. And it is by having access to the real data that then what you can show really becomes meaningful. Otherwise, the impact or the predictions may not necessarily reveal to be the right ones.
Yeah, I guess one of the other questions here, which is kind of relevant, is a broader question. There's questions about tree planting, but actually the question is about, could you put climate change adaptation goals into because at the moment your kind of life cycle assessment is focused on the climate change mitigation kind of targets, and there are other targets in that climate, and without having adaptation we won't meet this net zero. So is that something that you were thinking of, or is it possible?
Janet, would you like to go first?
Cool. So in terms of adaptation, it does also, so when we carry out life cycle assessment, we do look at policy in place and like what are the possible scenarios, but also look at behavior in terms of feeding that in terms of how would that work in terms of, so we do so it does, so we can consider it for scenarios. So it depends on like how would we move in the future, so that's how we could scope out our scenarios that way. So that's really what I can say in terms of, so even for like the reusable and single-use mask, we talk to our behavior guys and say like, what is it likely to happen? What is like whether it's likely that they'll use the mask or not, and what is to like scope out what scenarios we are. In terms of adaptation, it's kind of like how would in 10 years time, how would we progress in that sense? I guess this is why sometimes we do need to do like social analysis, also like economic projections to like understand like how would future scenario works, is what I'm going to say.
Thank you, Janet. So just final question then, as we're on the top of the hour, but I guess a question here is about whether LCA can be applied to any industry, like clothes manufacturing. What are the challenges? Who should be the stakeholders? How do we kind of you know, could we create a virtual circle for certification or something like that? Paola, do you want to have a go?
Oh, it can certainly be applied to absolutely any industry, and actually it has been applied already to textile. There is, for example, a very old study that looks at the LCA applied to a cotton T-shirt, and that is actually what we use in the classroom when we ask the students to think through, you know, the life cycle methodology, and we take the T-shirt and basically ask them to think about every single step of the process. And usually, you know, the coloring, the dyeing is obviously what has got the greatest impact. So it can definitely be applied to anything. And in relation to the stakeholders, it really depends on what question you're trying to answer. And whether it is to society to think that maybe we shouldn't throw away a T-shirt every 5 minutes, because that actually has an impact on the earth, you know, growing and harvesting the cotton, and then all the manufacturing of that into the actual T-shirt. Or whether it is speaking to the industry so that we can help them identifying what we call the hotspots, so the steps in the process that need to be looked at, improved, and perhaps totally transformed.
All right, thanks very much. I think there's so many questions left. I think Paola and Janet, you'll have to look them offline. But thanks so much for that absolutely fascinating insight into life cycle assessment. Really great. So I just think close the event now, but keep an eye out for the next one. But don't forget, there's a huge number of recorded sessions on YouTube, so you can have a look through those too, so you never miss an episode. All right, thanks very much, everyone, and have a good day.
Bye.